Yes, dear viewers, you are welcome to this session of physics with teacher Sabaiga Slide. Call me teacher Slide Sabaiga, your teacher tonight, who has come to introduce to you the beauty of motion. Our topic tonight is motion and all level topic. People are wondering what is all motion about. We are going to see today that by definition, yes, the topic we are talking about today. Oh, those who are viewing me and those who are in class, who can define for us motion? Those who have made research about motion, what is the concept of motion? Oh, I'm hearing people talking of movement. Exactly, that's what we are talking about. So we are going to realize today that motion, in simple terms, is just change of position with time. Change of position with time is the change of position with time. So what am I interested in here? Position with time. So in other words, mathematically, we are going to see that motion is going to be change in position. Change in position. Position with time. That's how we can convert this word statement into a mathematical formula. Change in position with time. What does this mean? Position in most cases is measured in meters. Change in position is distance. And then time is going to be seconds. So which means what we are going to deal with today, or what we are going to talk about tonight, is going to mostly deal with a change in distance or displacement with time in seconds. So a meter and a second are our units tonight. We are going to be much using the fundamental quantity of length and then a fundamental quantity of time, which is measured in seconds, which are all basic quantities. So people have wondered why motion today? It is because we can't move if it wasn't motion. Traveling in vehicle, the movement of vehicles is as a result of motion. Even your riding of a bike is as a result of motion. Somebody sat and thought about this physics. The movement of planes, people moving abroad, everywhere, that is motion. Can you imagine even my speech? When I'm speaking, I'm causing vibration of air molecules around my mouth. You see, when they vibrate, they have to move. Oh, this is very important. The motion is going even to knock into the medical and biological sector. Look at the circulatory movement of blood in veins and arteries. The biologists can tell us that is circulatory motion. People who enjoy sports, it is about motion. Athletics, football, the projectile form of motion. The watches which measure time and then the clocks, they describe a circular kind of motion, if not simple harmonic, as we shall see different, types of motions or categories. The rotation of the earth, have you seen? The earth, or the rotation of planets. For example, the earth is rotating around the orbit of the sun by a planetary motion, which is kind of circular motion by a centripetal force, which is directed towards the center of the sun. Can you imagine? The movement of air, and the air is all about life. So there are many reasons. I may not exhaust them tonight, but there are many reasons to why we are talking about the concept of motion. So dear viewers, the motion we are going to talk about today can be in form of trajectory, can be in form of rectilinear. Yes, rectilinear kind of motion, can be in form of vibratory kind of motion, It can be Brownian motion, that is for fluids, that is liquids and gases, and it will be in terms of circulatory, as we have seen, blood flowing into our veins and arteries. So this is a very wonderful topic to talk about. So why motion? Who developed this concept of motion? The concept of motion was developed by an Italian scientist, and this gentleman was by names of Galileo Galilei. Galileo Galilei. So this is a gentleman who developed the concept of motion some time back around the 16th century. So Galileo Galilei, this was an Italian scientist. He was a physicist, an astronomer, an engineer, the founder father of modern science. You hear American companies like NASA taking people at Mars, moving to different planets, out space. That is the modern science we are talking about, and that is kind of motion. Yes, the billionaires like Bezos, you heard him of recent. Yes, if you're following media, news, a gentleman who constructed his own, space rocket, which took him out space. And they are planning to start now making people move from Earth to out space in kind of, a tourism innovation. So that is it. So the kind of motion, or the concept of motion, having been started by Galileo Galilei, it was supplemented by what we call the father. This is the grandfather of physics or modern science. Then we have the father of physics. That is Sir Isaac Newton, an English scientist. So you need to go and make some research about these people. I may not talk about them today and exhaust them. There are a lot. If we talk about Galileo Galilei, how he formed telescopes in viewing, the moons of Jupiter. He did a lot. I may not exhaust him today. So, Sir Isaac Newton. So Isaac Newton. So, as it has been our mode of discipline, of introducing a topic, give you the background, and then finally talk about the real-life application. Today, the real-life application for motion are visible, and I give you that homework. This is not an abstract topic. It has its applications. Go and make research about the real application. But again, I've mentioned about them already. So, Sir Isaac Newton, a gentleman who died on 25th of December 1642. 25th of December, when people are jubilating Christmas, some of us, the scientists, we are crying, commemorating Sir Isaac Newton, a gentleman who attributed to the growth of physics. Can you imagine? When he was in London during breakout of a particular disease, which was plague in London and the whole Britain, this gentleman went to his mother village, that is Woolsworth. So he was seated in an apple tree. An apple came and fell onto his head. Then he started asking, why didn't this apple move upwards? Why did it come down? That was the origin of Sir Isaac Newton's discoveries about motion. And whatever he discovered, he compiled it and put it in a particular book, the Principia Mathematica, Philosophy. You go and make research about such a book. So, today, it is about motion. It is the concept of motion. Hope this humble beginning has made you like the concept of motion. Now, when I come back, I'm going to show you what I'm supposed to be in position to tell at the end of this topic. You as a student, what do you expect at the end of this topic? Immediately after a break, Teacher's White is coming back with such. Stay tuned. Yes, my dear viewers, we'll be back from the break. Hope you've enjoyed the definition and then the humble beginning of our concept of motion. Now, at the end of this topic, each student, each of you should be in position, first of all, to, this is what I expect you to know at the end of this topic. So I expect you to define some of the terms which are used here. Oh, let me divide my board. So some of the terms I expect you to be knowing and to define very well are going to be distance. I expect you to be knowing the meaning of distance, the meaning of displacement. These two are not the same. The meaning of displacement. What is displacement? What is distance? I expect you to be knowing that. I expect you to be knowing speed. So, in other words, this is the course outline or the topic outline, what we are going to talk about in this arrangement. So, I expect you to be knowing about speed, then to be knowing about velocity and distinguishing between each of these pairs, between distance and displacement. How can you distinguish between speed and velocity? I expect you to be knowing that. Then I also expect you to be knowing a concept of acceleration. Acceleration. You always hear of the accelerators in manual cars, so it is here tonight. I expect you to calculate average speed. Do you know how to calculate average speed? Do you know the correct formula for calculation of average speed? That average speed is given by total distance over total time, from the concept of mathematics. I expect you to be knowing that. I expect you to plot and interpret what we call speed time graph or distance time graph. So, will you be in a position to plot what we call the speed and then time graphs? There are very many. Can you go and plot and also explain to us what we call the distance time graph or time graphs? There are very many. Can you go also and explain to us the velocity time graphs? Velocity time graphs. All that is expected here. I expect you at the end of this topic to recognize from the shape of maybe a speed time graph. When a body is at rest, we are going to know words like rest. When we talk of rest position, that is no motion, no movement. So compare the word motion with movement. Things like, if you have plotted a speed time graph, can you describe from the shape of that speed time graph when a body which is describing such a time graph is at rest? Can you describe when that body is moving with a constant speed? So we shall get to know the word constant speed. Not only knowing the definition of speed, but also constant speed. Can you tell us when a body is moving with changing speed? What are the implications of changing speed? Do you know that when the speed is changing, it brings about what we call an acceleration? A body accelerates. When a body is moving at a constant speed, will you get to know that this body is now moving with a zero acceleration? And from our concept of force, do you know that when the acceleration is zero, resultant force is also zero? When a body is moving at a constant speed, it means the acceleration is zero and the constant force is also zero. At the end of this topic, after plotting these graphs, I expect you to calculate the area under a speed time graph or a velocity time graph to work out the distance traveled for motion with constant acceleration. So which means we shall talk about what we call constant acceleration. Have you seen constant acceleration? So clever students have already started picking these terms and they are emphasizing them. They are taking screenshots. They are printing screens and pasting into their Word documents. And now they are moving to Google search to make research about all these. Such that when a teacher starts to explain, they are well versed with everything. Still, at the end of this topic, I expect a student to demonstrate understanding that acceleration and deceleration are related to changing speed, including qualitative analysis of gradient of speed time graph. So another word here is coming, and that is deceleration. Mostly deceleration. So will you go and compare deceleration to acceleration? Is there any difference between deceleration and acceleration? Will you get to know that deceleration is also called a retardation? A retardation. That's what we expect from you. Every topic in physics has some expectations from the teachers and examiners. When we are examining, we base on those expectations. When we are bringing questions for you, we base on those expectations. So whichever topic you get introduced to, know what examiners expect from you. What are you supposed to do? Can you distinguish between velocity and speed? We expect that. Can you define and calculate acceleration using change in velocity over time taken? We expect that from you. Can you calculate speed? If we have a distance time graph, can you use this distance time graph to calculate speed by a method of finding what we call the gradient, which is a mathematical formula, or what we call slope in physics? Can you go ahead to state the equations of uniformly accelerated motion? Equations of motion. Equations of uniformly accelerated motion. Uniformly accelerated motion. So, however much we talked about many categories of motion, trajectory, vibratory, rectilinear, ours is going to be a rectilinear form of motion. That is motion in a straight line. So our topic would have been motion in a straight line mostly. At this level, you don't need those other forms, like the trajectory motion, you don't need it. You need motion in a straight line. I was saying that, can you go and talk about the equations of a uniformly accelerated motion? Can you tell us that when we talk about deceleration or retardation, is the negative value of acceleration? Can you describe qualitatively the motion of bodies falling in a uniform gravitation field? Do you know what we call gravitation or a gravitation field? What if these bodies falling in a uniform gravitation field are falling without air resistance? What if they are falling with air resistance? Do you know that there is terminal velocity? Have you ever imagined the motion of a parachutist who jumps off from a fast-moving plane and is being immersed into a fluid, which fluid is going to be air, which air offers resistance, and then some upthrust, and his weight is driving him downwards. But how comes that this parachutist lands safely onto the ground? Is what we have come to introduce today. Yes, people who have ever gone to exhibitions, you have seen motion of different gadgets. You know, they are moving, but that is circular kind of motion, which we may not talk about here today, because for us we need motion in a straight line. Motion in a straight line. You see? Can you go and talk about what we call terminal velocity for a body which is falling maybe into a viscous fluid, a fluid which offers resistance, which fluid resistance is called viscosity? You see? Can you talk about, can you describe experiments to determine acceleration due to gravity? But again, what is acceleration due to gravity? What if I twist it and call it free fall? free fall. Free fall. All that's what we are going to talk about in this concept of motion. We are going to go ahead and talk about, if I can clear some space here, we shall go ahead and talk about what we call impulse and momentum as a result of motion of different vehicles, interaction. You see, impulse. Have you ever heard of the word impulse? Impulse. And this is the same as change in momentum. And do you know what we call momentum? Momentum of a body. Can you talk about Newton's laws of motion? Oh, Newton's laws of motion. Sir Isaac Newton is now coming in. That's why I talked about him in the preamble. So, Newton's laws of motion. Newton's laws of motion. Have you ever been in a lift? Do you know how some of the Newton's laws, or one Newton's law is applied? Or two, they are applied for the motion of a lift or person who is in a lift. Oh, so we shall talk about that. Yeah? Motion in a lift. Motion in a lift, or of a lift, or motion of a lift. We can make it of a lift. Have you ever gone for training, army training? In some countries, yes, strong men have to go and serve their countries, and you have to hold a gun. But once you fire a bullet, do you know that it performs what we call a recoil velocity? As the muzzle fires a bullet, then there is a recoil velocity, the recoiling of the gun. So, motion of the gun, recoil of gun, recoil of the gun, etc. So, this is our topic outline. That's what we expect you to be knowing up to this end. From where we started, the distance, up to now the recoil of the gun. You need to be knowing all those particular aspects. So immediately after a break, my beloved viewers, I'm coming back with some of the terms used in this concept of motion. I've already mentioned them, but now we are going to see their definitions. Stay tuned. Dear viewers, we'll be back from that wonderful break. So Teacher's Light is still your teacher. Tonight, taking you through the physics of motion. So, I'm teaching students at different curriculum levels. Those who are at the local curriculum, all what I've mentioned here, you have to study it, and that's what we expect. Then people who are on the Cambridge curriculum, yes, things to do with the recoil velocity of the gun, things to do with motion in the lift, things to do with the Newton's laws of motion. You may not actually talk about them. They are out of your syllabus. I'm talking about people who are on the IB CSE curriculum. That is the Cambridge curriculum. You may not talk about that. So let us go and talk about the terms used in the concept of motion. Terms used. Terms used in motion. In motion. Terms used in motion. So the first very term is what we call distance. Distance. So dear viewers, what is distance? Someone tells you to define that. Oh, some people are giving me answers. They are telling me that that is the length between 2 points. Very good. So that is a good definition. So distance is the length. Is the length between 2 points. Length is a fundamental quantity, and you know its units. So you can state the SI unit of distance. So SI unit of distance is, tell me exactly, is a meter. is a meter. So a meter, at the beginning of this level, we talked about the different quantities. We said a quantity is an observable property, and we stated the unit of a meter, of length, which is a meter, and the symbol is small m, not capital M. The moment you write capital M, we shall not mark you. Remember, physics is a practical subject. So you have to note distance. Why are we defining these terms? It is because we are going to use them in this concept of motion, slowly by slowly. Now let us go and talk about another term similar to distance. So this term is what we call displacement. Oh, displacement. If I happen to put my phone here and a student picks it and hides it maybe in a desk, oh, which is very bad. My phone has been displaced. It has been displaced. So dear viewers, what is displacement? Yes, students in class, can you tell me what displacement is? Oh, distance moved in a specific direction. Wonderful. So that is the correct definition. So displacement is the distance moved. Is the distance moved in a specific direction. So I want you to underline the word direction. Yes. What makes displacement differ from distance? Here, you are moving a particular distance in a given direction. So we are going to see that displacement is a vector quantity. Previously, we talked about vectors and scalars. We say that a physical quantity with both size and direction is called a vector. Size is what we call magnitude. Then a physical quantity with only size or magnitude, like a kilogram of sugar, will remain a kilogram of sugar. Even if it is in the western direction, make it in the northern direction, it will remain a kilogram of sugar. So mass is a scalar quantity. It has no direction. So a quantity with only magnitude or size, we call it a scalar quantity. What I'm talking about is scalar as in this, scalar. So this is a scalar quantity. Distance is a scalar. Then this is a vector. This is a vector quantity. The distance is very important. Very important. Which means displacement can be negative. Yes. If at all I've been moving in this direction, that is my original direction. Once I reverse it, then that is a negative displacement. The distance in a given direction has been altered. So we shall find some distances with a negative sign, but those are distances in a given direction. And that is what we call displacement. Whereas distance, a scalar quantity, cannot be represented by negative. You cannot say that I'm very short, or the distance from here up to UK is negative something miles. No, that is wrong. It can't be. So the major difference between distance and displacement is that displacement is a vector quantity, whereas distance is a scalar quantity. You need to note that down. Note and say that the major difference between distance and displacement is that distance is a scalar quantity, whereas displacement is a vector quantity. Now, our physics is very funny. Somebody may tell you to distinguish. Have you heard the word? The word is distinguish. Distinguish. You know, this is a subject which makes engineers. So we are very serious when we are marking you. A single mistake is going to cost you a mark. So when we tell you to distinguish, this is a language of physics. We distinguish by definition. You distinguish any two physical quantities by defining each of them. Different quantities will never have the same definitions. Their definitions will be totally different. So, when we try to distinguish, give the difference by definition. However, if we tell you to give differences, if I tell you give a difference between distance and displacement, you can pick out what I've just said. That distance is a scalar quantity, whereas displacement is a vector quantity. Have you seen the difference? Then you can also give another difference, a difference of definition. Yes, it's also, you see, very interesting. And differences, we normally give them with a table of distinguishing characters. For example, if I'm differentiating between distance and displacement, then I'll draw a table with two columns. One quantity on one side, if this is distance, and then displacement on the other side. Then I talk about one distinguishing character at a time. If I'm talking about direction, that distance has no direction, displacement has direction. I'm talking about direction in that row. That is my distinguishing character. It is direction. If I'm talking about SI units, if at all they are different, talk about them. But here, the SI units are going to be the same since displacement is the distance moved in a specific direction. So allow me to talk about the term number 3. I'm rubbing off. We are looking at the terms used in our concept of motion. So term number 3, can you guess term number 3? Yes, from your junior science, you talked about speed. And everybody here has ever been driven at a given speed, or you have ever moved at a speed. So, dear class, what is speed? Can you define for me speed? Speed. Oh, so what is speed? People are fidgeting. Oh, somebody is giving me an answer. What is speed? Oh, she's saying change in distance. Yes, change in distance. Moved, yes, with time. Good. Yes, you can't hear her, but I can hear her. Yeah, so that is it. Speed is about change in distance. If the distance you are moving can change, possibly in the possible minimum time, then your speed is very high. So in physics, we are going to say that speed is the rate of change. Is the rate of change of distance with time. With time. Or we can say that speed is the change. Is the change in distance moved. In distance moved with time. With time. SI unit is going to be picked from a formula. So we are going to see that the speed we are talking about here has already been given a mathematical interpretation, because the examiner has talked about rate. The meaning of the word rate in physics does not specifically mean time, as the chemists confuse it, as the biologists confuse it. In biology or chemistry, the moment you talk about rate, their minds go with time. Onto time. It's not the case with physics and math. These are unique subjects, because those people of biology and chemistry, they borrow our words without exactly knowing when do we use them. So rate is just a variation of two quantities. What do I mean? Take an example of a quantity like diameter varying with radius. Assuming at a time t1, I have a circle of that nature. This circle has a radius r1. and its circumference C1. And then at a time t2, yes, as time passes, the circumference increases and the radius automatically will increase. This is R2C2. So if we want to compare circumference with radius for this variation, for this rate of change, then we can say the rate of change of circumference with time. And mathematically we read this as with radius, sorry, time is not a factor here. It's not a major factor. I'm comparing circumference with radius. So this is a rate of change of circumference with radius. That is dCdr. There is no time here as a major factor. You see? So if your concept now, what was in your head was that a quantity has to vary with the time so long as somebody talks about rate, that is wrong. So what does this mean? Whenever you're going to use the word rate in your definition, you need to show us the two quantities which are varying. However much time is the one which is in that particular, among those particular quantities which are varying, you need to tell us that time. So what am I trying to say? On the internet, in certain pamphlets written by teachers like me, by different authors, you are going to encounter different definitions of speed in this concept of motion, and even different definitions of velocity and acceleration. When these people are mentioning only one quantity, remember I told you a quantity in physics is an observable property. So what does this mean? If I tell you that speed is the rate of change of distance with time, and for you come and tell me speed is the rate of change of distance, because you know rate is time, that is a biology outlook or a chemistry outlook. We are not going to give you marks here, because for us we define rate as variation of any two quantities. So you are supposed to use the word rate when you are talking about two quantities. Hope I've explained this quantitatively clear. And as semi-candidates, I expect you now to absorb my words. My teaching is always a copy and paste. You copy from my mouth, paste into your brains. That was a joke. Let us proceed. So, mathematically, we are going to see that speed is distance over time. So, any quantity which is a derived quantity, which is formed by a mathematical formula, that quantity is easy to obtain its units. The units are going to be obtained or derived by multiplication or division, depending on the formula where the quantity comes from. So the quantity of speed comes from distance and time, and it is division. So we are dividing distance, which distance is in meters. Distance, SI unit, we say in meters. And then time, which is in seconds. So SI unit is now going to be a meter divided through by a second. Now we talk in terms of units. Previously we talked about quantities. We are looking for the SI unit of this quantity, speed. But we are dividing distance in meters over a second. So we can read this and say meters per second. Can everybody say meter per second? Actually not meters, but meter per second. So SI unit of speed is meter per second. Small words. And how do we abbreviate this? We abbreviate it as meter/seconds. Or we abbreviate it as meter s power -1 from the mathematics of indices. Let us go and see. How does a meter/second again becomes a meter second power -1? Let us go and see that algebra of indices, such that people get to know why do we recommend this. In our practicals, we shall recommend these indices, the power, not the slashes. A serious student has to understand that today. So let us go and see that. That is a mathematical proof. A mathematical proof. So the proof is here. Why do we say that m over a second? You know, meters per second is the same as meter divided by a second. We got it from here, distance over time. So this is the same as saying a meter times 1 over a second. There's nothing I've done there. It is just mathematics. Because a meter times the numerator 1 will give me a meter over the denominator s, which is a meter over second, or meter slash second. And an over sign can be in this format or in form of a slash. So me, I've used this and nothing I've done there. But from indices, once I see any division, I just know that once we divide elements on the same base, then we can raise to one base and subtract the powers. That is second law of indices. So which means there is a need to make 1 to be in terms of base s, because I'm seeing s power 1 already here. But any number power or any element power 0 is 1, which means this 1 maybe came from s power 0, such that now I'll go and get m times s power 0 over s power 1. There's nothing I've changed. It is still the same. I'm just playing on math, because s power 0 is 1. S power 1 is the same as s. From the second law of indices, when I'm dividing elements on the same base, raise to one base, subtract the powers. Let me do that. So this gives me m times s power 0 minus 1. Raise to one base, subtract the powers. The numerator power minus the denominator power. So 0 minus 1, dear class, what do you get? Oh, people saying negative 1. So the overall thing is coming here, is going to become meter times s. We are remaining with a negative 1. So we can remove this sign and then remain with what we call a meter per second. Meter per second. We first read the power before we read the base. That is the correct way of reading these indices, units in terms of indices, which appear as indices. So, what are you supposed to note in the concept of speed? Definition of speed, mathematical interpretation of the definition of speed. How can you derive SI unit of speed? That's what you need to know. And then also you need to talk about what we call average speed. So, let me rub off here and then we talk about average speed. So, dear class, what is average speed? Yes, that is correct. So, average speed is total distance over total time. Total distance over total time is what we call average speed. Average speed. Very wonderful. Marvelous. Okay. So, average speed is in our LB. So average speed by formula, because we shall always calculate average speed, is equal to, this is average speed, is equal to, oh my watch is disturbing me, so I don't know why the screw doesn't, fix into, so the average speed is equal to total distance over what we call the total time. So average speed will still be measured in meters per second because it is distance over time, however much we are using total time. So total distance over total time. Now this takes us to another term, and this is term number 4, and that is what we call velocity. Velocity. Can everybody pronounce this as velocity? Velocity. So, there are some people here who are called Veronicas. This is not your city, yeah? Yes, you have started bragging that this is velocity. No, this is a science word. It is velocity. It is velocity. So, dear members, what is velocity? Oh, I can see people in my class are trying to raise up hands. Yes, can you try? Change in displacement over time taken. Very good. So velocity is the time rate of change of distance in a specific direction. The distance in a given direction, which we are calling displacement, is changing with time. Meaning that velocity is a vector quantity because it is given by displacement, which displacement is affected by direction. So we can define velocity as is the time rate of change of distance moved in a given direction, or of displacement. So the two quantities which are needed here, time and displacement. As we use the word rate, we need to talk about the two physical quantities which are there. Or another person can define velocity as velocity is the distance moved in a given direction in a particular amount of time, or the rate of change of distance moved in a specific, this is a marking point. If you stop on distance, then you're talking about speed. You're not talking about velocity. Distance moved in a specific direction with time. With time. So that's how we can define velocity in another kind of arrangement. So velocity is the rate of change of distance moved in a specific direction with time. Or we can say velocity is the rate of change of displacement with time. Or velocity is the time rate of change of displacement. Have you heard that? Oh, so therefore velocity is just the speed in a given direction. Have you seen the relationship? Speed in a given direction. If you are moving at a given speed and you are most interested in the direction, then what you are moving with is not only speed, it's velocity. I don't know whether people have got me. Oh, very interesting. So therefore, we can note that therefore, velocity is the speed in a given direction. Once the speed is given direction, remember speed is a scalar quantity. What makes it to be a scalar quantity? It is given by distance, which is a scalar quantity, and time, which is also a scalar quantity. So there's no way it can become a vector quantity. So if the speed is a scalar quantity, once it is given direction, it ceases to become or to be a scalar quantity, but rather now becomes a vector quantity. And it will no longer be called speed. It is going to be called velocity. So mathematically, yes, velocity is equal to displacement or distance moved in a given direction over time taken, over time. That's what we call velocity. So since distance moved in a given direction is measured in meters and time is measured in seconds, then it means velocity is measured in the same units as speed. Those units, we talked about them as exactly meters per second. So we come and say that SI unit, the standard international unit, SI unit of velocity is meter per second. Meter per second in that format. That is the SI unit of velocity. Now, NB, note this with a lot of carefulness. The difference between velocity and speed is very clear. I've already talked about it. So the major difference between speed and velocity is that velocity is a vector quantity. Just like displacement. Whereas speed is a scalar quantity, just like distance. And the common unit, or the common similarity, or the similarity, is meter per second. They are all measured in meter per second. That is the similarity. You see? So if I try to distinguish between velocity and speed, use definition. If I try to give differences between speed and velocity, draw a table of distinguishing characters. Put one quantity on the left-hand side and put another quantity on the right-hand side of your table. Then start giving the differences, talking about a given or a common distinguishing character. So immediately after a break, we are going to see other units in which speed and velocity are measured, because people have started complaining that, again, teacher, for us when we are driving, the speed is in kilometers per hour. Then for people who are racing, the speed meter is calibrated in miles per hour. Aeroplanes, miles per hour. Oh, rockets, miles per hour. Those are just other units, but not the standard units. There are some standard, international, which we as physics scholars agreed. We send representatives to UK to recommend international standards in different aspects. So for the aspect of units, there are some international standards in the UK. That is the base where they come from. And then they saturate. For example, if you look at length, some people can measure length in terms of feet, but that is not standard. We need to establish a standard unit, and that is a meter. You go to Vietnam, they will tell about a meter. You go to Afghanistan, they will talk about a meter. They know that 1 meter is equivalent to 100 centimeters. So they know a standard unit of measurement of length. So the same applies to these other quantities. They are derived units, but now the fundamental quantities whose SI units are considered, they come and dictate. Like speed comes from distance, which is length and time. So the meter and the second are going to dictate the units of speed and as well as velocity. So if we have other units of speed and velocity as maybe kilometers per hour, then how can we convert to SI units, or from SI units to derived other units? That's what we are coming back for. Stay tuned.